Good morning, class, and welcome to another lecture in sustainable energy technology. We will today continue our discussion on hydropower plants and hydro turbines. In the previous class, we started our discussion of impulse turbines, which has been shown in this figure, which we discussed in the last class as well. So in an impulse turbine, just as this schematic, which shows a type of impulse turbine which is called a Pelton turbine, the water that is coming from the penstock through penstock tunnel is directed into a set of nozzles which converts the pressure head of water into velocity head, and hence a high velocity jet of water is directed towards the Pelton wheel, which contains cups into which this water enters. In this, there is a transfer of momentum from the water to the wheel through the impact of the water jet into this cup-like structures. So what we have here then is water is accelerated through a set of nozzles which generate high velocity of jets of water, which are incident on bucket-like blades of the impulse turbine rotor. And the blade design is such that there is a maximum transfer of momentum from the water jet to the rotor wheel, and this results in the transfer of kinetic energy from the jet of water to the rotor wheel. As a result, the wheel rotates, and this is connected to the generator shaft, and hence it generates electricity. As we discussed, impulse turbines like Pelton wheels are suitable for locations where the water volume is low, because you can only arrange a few jets, maybe 3 to 6 jets around the wheel of an impulse turbine, and hence it constrains the amount of water you can actually flow through your system. So small rivers with low volumes of water flow and which have high heads, which can be converted to high velocity jets, is the most effective places where impulse turbines and Pelton turbines can be installed. So these are good for small hydropower in hilly regions where large elevation changes occur naturally. What we see here, and we will discuss this later as we look at some of the derivations, is that this is the total head height between the top of your river and where the nozzle is located. Now, during this flow of water from the reservoir through the penstock to the channel and through the nozzle, there will inevitably be frictional losses. And these frictional losses can be converted into a head loss. So HF is the frictional head loss. So the actual head available for conversion from kinetic energy of the nozzle jet to the kinetic energy of the rotor wheel of the Pelton turbine is total height minus the frictional head height loss, which is the available head HA. And we will discuss this available head HA in the next set of derivations. Two other things that you can notice, that the supply pipe that goes through the penstock, as you remember, this is the kind of the supply pipe region, and this is the area of that supply area, which is called the penstock. Suppose that area is A, and the nozzle that generates the jet of water, that jet of water will have a diameter, a cross-sectional area as well, and this is called A suffix J. Okay. So these are some of the actual figures of these kinds of nozzles that are hitting the Pelton wheel. This is an actual, again, you can see it's a large Pelton wheel, an actual photograph of an operating Pelton wheel. So these are still widely used in many parts of the world. Here is a design from General Electric of such a Pelton wheel based turbine. So next up, what we will see is the Pelton turbine principle, and we will look at a mathematical derivation which gives us the maximum possible power that you can extract out of a Pelton turbine. Okay, given a certain water volume and given a certain available head for that water. Now here, what is being shown here is this bucket shaped wheel, this kind of a dual leaf kind of a structure. This is the cup or the wheel or bucket that is attached to the Pelton wheel rotor. So these ones, okay. This jet of water hits the center ridge of this cup head on, and then this water flows through the outer edges of this bucket and exits the bucket at the edges. Okay. So here Qj, so this should be Q suffix j, is the volume flow rate of a given jet of water in meter cube per second. Okay. Uj is the velocity of this water jet that is hitting your Pelton wheel bucket. Uc is the velocity of the cup as the Pelton wheel is rotating because of the impact of these jets. So it has a certain velocity. So the cup itself is moving at a certain velocity uc, which is the cup velocity. Okay. And u2 is the exit velocity by which the water is leaving the cup at the edges. Okay. So those are the three velocity vectors that are relevant for understanding the movement and the momentum transfer of this water jet. And this is in the stationary frame of reference. So now if you look into the same picture, but now in the reference frame of this moving cup. So you are sitting on the cup, with the cup is moving, and you are looking at the velocities with respect to the cup. Then the relative velocity of the jet with respect to cup is uj minus uc, and the relative velocity of the exiting water is u2 minus uc. Correct? Because you are sitting with you are evaluating these velocities with respect to the cup only. Okay. So ur1 is the relative velocity of the jet with respect to the cup, and ur2, which is equal to u2 minus uc, is the relative velocity of the exiting water with respect to the cup. Okay. Now we can show that when you want to have the maximum momentum transport, then the inlet and the exit relative velocity of the jet with respect to the cup must be equal and opposite. So you are sitting on the cup, so the maximum momentum transport, the water directly enters and then directly leaves in the opposite direction. So the velocity of the water with respect to the cup is incoming and the outgoing velocity are exactly opposite of each other. So one goes along the plus x and one goes along the minus x with respect to the cup. Then you have the total, the maximum possible transfer of momentum will happen. Okay. So if the inlet velocity with respect to the cup is uj minus uc and the exit velocity with respect to the cup is u2 minus uc. So for maximum momentum transfer, these two should be equal and opposite. So uj minus uc will be equal to minus of u2 minus uc. Okay. So this is the maximum possible momentum transfer happens under this condition. Then the force experienced by the cup due to this net change in velocity is basically the mass of the water jet into delta v, where delta v is the change in velocity. Now what is delta v here? Delta v is the final initial velocity minus the final velocity. So this is 2 times uj minus uc, because these are equal and opposite of each other. Correct? So the delta v, the change in velocity, is 2 times uj minus uc, and the mass flow rate is density of water into the volume flow rate of the jet. So rho of water into q jet. So the total force experienced is the change in velocity into the mass flow rate. Okay. This is the force on the cup. So the power transferred to the cup is force into the velocity of the cup itself. Okay. So power is basically rate of W dot. Okay. So W is basically integral of f dx. So W dot is integral of f dx by dt, which is integral of f d of velocity. So if you do the integration, then the force into the velocity of the cup gives the power that is being transferred from the jet to the cup. So this is this F force into the cup velocity. So this becomes twice rho Qj, Uj minus Uc into Uc. So this is the power transfer under the maximum possible momentum case, momentum transfer case. Now, for a given jet velocity, the power is maximized when this power transfer Pj divided by del Uc becomes equal to 0. So here what we are saying is the jet velocity is kept constant. Okay. And the jet, of course, the density is constant and the jet volume flow rate is constant. So the only thing then, this power Pj being transferred to the cup, to the Pelton wheel, depends on is the Pelton wheel velocity Uc. Correct. So if you take a differential of the power with respect to the Pelton wheel velocity Uc and set it to 0, you get the maximum volume value. So it's basically the maxima of the power transfer. This is given by del Pj by del Uc equal to 0. So if you do this differentiation and set it to 0 in this expression, then you will get the final expression as the ratio of the cup velocity by the jet velocity will be equal to half. Okay. So what this means is the cup velocity Uc must be equal to half of the incoming jet velocity Uj for the power transfer to be maximized. Okay. So under this condition, Pj max will be half rho Qj Uj square. Why? Because you have Uj minus Uc. Uc is Uj by 2. So this becomes Uj by 2, and so this becomes Uj by 2. This one here, and Uc also is Uj by 2. So you have Uj square by 4, and this is 2. So it becomes half rho Qj Uj square. So the maximum power that can be transferred to the Pelton wheel bucket is half into density of water into volume flow rate of the jet into the jet velocity square. Okay. Notice here that when Uc by Uj is equals to half, right? Then Uj minus Uc becomes equal to Uj by 2, correct? So then, and Uc is Uj by 2. So minus U2 plus Uj by 2 will be equal to Uj by 2. So U2 will be equal to 0. So under this maximum momentum transfer condition, when Uc by Uj equals to half, the exit velocity Ut will be equal to 0. What this means is there is no exit velocity component along the direction of the impinging jet. Okay. So basically what happens is the water goes like this and flows in the y direction because it's incoming in the x direction. So the component of Uj along the x direction is Uj completely. The U2 will have no component of velocity in the x direction at all. So that's why U2 is equal to 0 in the x direction. Of course, water will flow out, but that water will have no velocity component along the direction of the impinging jet. Okay, so that's what U2 equal to 0 means. Okay, this is of course a very idealistic situation. What this kind of means is U2 is basically going perpendicular downwards. Okay, that's why there is no velocity component in the x direction in this condition. Now we have found this very important condition that the cup velocity will be half of the jet velocity for maximum power transfer, which becomes half rho Qj Uj square. Now what is jet velocity? Based on Bernoulli's equation here, Uj, and this is the initial total available head Ha of water, and this is entirely getting converted into the jet velocity Aj, correct? So based on the Bernoulli's equation, Uj will be root over 2g into Ha. So that is uj square is equals to twice g into the available head of water at the nozzle level. Okay. So here half rho qj uj square, you can also write half rho qj into 2gha, which is the available head of water. Okay. So the maximum power directly depends on the available water head that is present. Okay. So suppose, of course, a Pelton wheel will have more than one nozzle. So there will be 3, 4 or 5 nozzles present. So suppose the number of nozzles around a Pelton wheel is n. Okay. So the total volume flow rate of water through the penstock is equals to n times the volume flow rate of individual jets, n times qj. And qj is the velocity of water into the cross-sectional area of the jet. So the total volume flow rate Q is n times the area of the jet into the velocity of the jet. Okay. Furthermore, there will be a mechanical efficiency associating with conversion of jet momentum to shaft rotational power, because the shaft will also have frictional losses, and this splashing of water along the bucket will also cause a lot of frictional losses during this momentum transfer effect. So there is an efficiency by which this jet momentum can actually get transferred into the momentum of the Pelton wheel. So this mechanical efficiency we are calling eta m. Okay. So the total power generated, so that all the efficiencies from the transfer of jet momentum to the final generation of power is clubbed into this eta m mechanical efficiency value. So the total maximum power generated is equals to this mechanical efficiency eta m into n times the power transferred by a single jet. So eta m into n into pj. Okay. This is the efficiency term. This is the number of nozzles. So each nozzle has a certain momentum that is being transferred, and this is the total jet momentum power transfer due to jet momentum under idealized condition Pj, which is given by this expression here. Okay, power transferred by the jet. And again, this under ideal conditions becomes eta m into n into half rho aj uj cube. How do we get this? The maximum Pj max is half rho qj uj square, and what is qj? Aj into uj. So this becomes half rho aj uj cube. This is the expression that is given here into the number of nozzles into the mechanical efficiency. And then you can replace uj cube by 2jha to the power 3 by 2, and this has been done here. So the final power generated by a Pelton turbine under given a mechanical efficiency eta m and number of nozzles being n is given by this expression here, P max half eta m into n into aj into rho into 2gha to the power 3 by 2. Okay. Where eta m is the mechanical efficiency, n is the number of nozzles, aj is the jet cross-sectional area, rho is the density of water, 2gha to the power 3 by 2 is the ha is the available head. Okay. Usual number of nozzles is between 4 and 6. Here note that the angular velocity of a Pelton wheel is basically the radial velocity you see by the radius of the wheel r, or if you put uj by 2 instead of uc under the ideal conditions, so it becomes uj by 2r. Okay. Note here, the total volume flow rate through the penstock will be either less than or equal to the total volume flow rate of the river. Okay. Either the entire volume of the river is going through the penstock or a part of it is going through. So the Q of the stream will be greater than this total Q that we evaluated here, which is equals to n into aj into 2gha to the power 0.5. Okay, as we have discussed here. Okay. Now, as we said, the Pelton wheel radius is r. Okay, so the Pelton wheel bucket velocity you see is r into omega. Okay, but at maximum power, uj is twice uc, and uj is root over 2ha, and UC is R omega. So root over 2GHA equal to twice R omega. So this gives the radius of the Pelton wheel itself can be expressed in terms of 0.5 root over 2GHA by omega, where omega is the angular velocity of the Pelton wheel, radians per second. Okay. So this is the expression of what the radius of the Pelton wheel is going to be under the maximum power condition. Okay. Similarly, we can also get an expression for the jet radius. This cross-sectional area AJ is also, you can think of it as a circular cross-sectional area. So AJ is equals to pi RJ square. Okay. And the total power P max is half eta n AJ rho 2GHA to the power 3 by 2, where AJ you can replace by pi RJ square, put RJ square on one side, and then everything becomes the maximum power by root over 2 eta n rho pi GHA to the power 3 by 2. Okay. So basically we have just put all of these things here, and we have put RJ square here, and everything else we have put in the denominator. So then you have an expression for RJ and an expression for capital R. So the ratio of the jet radius to the bucket radius, RJ by R, can be expressed now, and this, the final expression becomes equal to 0.68 into what is called a shape number S by root over mechanical efficiency eta m into the number of nozzles n. Okay, and this shape number S is a important design factor often used in Pelton wheel turbines, and is given by the rotational speed of this Pelton wheel in radians per second, root over of maximum power by density of water into GHA to the power minus 1.25. So this is the shape number of a given Pelton wheel working at a radius omega. Okay, and you can put the shape number here, and you will get the ratio RJ by capital R for a given mechanical efficiency and given number of nozzles. So that will help you design your Pelton wheel turbines. Okay, that what is the radius you need, what is the angular velocity you need, etc. Okay. So in the next class, we will also look at a few worked out examples that can help you use these formulas to get good design data for a Pelton wheel turbine.